Welcome back to the Deep Dive. Today we are stripping away the philosophy and getting right down to the hardware. We're talking about consciousness. And I don't mean the who am I existential crisis type of consciousness, though, we might get there by the end. I mean the mechanical, the electrical reality of being on.
It's one of the strangest disconnects in human experience, isn't it? To you, listening right now, your own consciousness feels like a river.
Yeah, it just flows.
It just flows, it feels continuous, one thought bleeds right into the next, seemingly without any interruption. But if you actually look at the schematics, if you look at the physiology, that is, well, it's an illusion.
It's not a river.
It's not even close. Under the hood, your consciousness is a series of discrete, distinct electrical states. It's a switching mechanism. It's all about rhythm. And today, we are going to tear that mechanism apart to see how it works.
To do that, we are pulling from two absolute heavyweights in the medical canon. We've got Genong's Review of Medical Physiology and Guyton Hall's textbook of medical physiology.
The cornerstones.
And I think it's worth setting the stage here because these two books, they approach the brain very differently, don't they?
Oh, completely differently. I always think of Ganong as the mechanics manual.
Yeah.
It's gritty. It wants to talk about the voltage-gated ion channels, the molecular switches, the specific cellular gears that make everything turn. It's obsessed with the parts.
And Guyton.
Guyton is the systems engineer. He steps back and looks at the flow, the big picture. How does the thalamus talk to the cortex? How does the hypothalamus regulate the timeline for the whole body? It's all about homeostasis and balance and regulation.
So our mission today is to synthesize these two views, the microscopic and the macroscopic, to build a map of the sleeping and waking brain.
Exactly.
Now, before we cut into the brain, a quick disclaimer. We are building a conceptual scaffold here. We are interpreting and synthesizing a massive amount of incredibly dense material. If you are a medical student or a clinician, this does not replace reading the chapters. You absolutely still need to put your eyes on the text.
Absolutely. Think of this as the color commentary. It helps you understand the game before you go back and study the play-by-play. The goal is that when you do read the text, these concepts we discuss, they act as anchors for all those details. It makes the reading deeper.
Perfect. So let's start with the fundamental problem, the on-off switch.
Right.
We perceive sleep as the brain turning off. I pull a plug, the screen goes black, I wake up 8 hours later. But that's dead wrong, isn't it?
It's completely wrong. I mean, think about it. If your brain actually turned off, you'd be dead.
Okay, fair point.
Energy consumption in the brain barely drops during sleep. In fact, in some stages, like the dreaming stage, REM sleep, it actually goes up. It's higher than when you're awake.
So sleep isn't about stopping activity.
No, it's a reorganization of activity. It's not unplugging the TV. It's just changing the broadcast frequency.
Okay, to understand that frequency, we have to talk about the instrument we use to measure it.
Yeah.
The EEG.
The electroencephalogram.
The famous brain waves. We've all seen it in the movies, right? The patient lies there with all these wires glued to their scalp, and there's a monitor with these squiggly lines bouncing across it. Now, I always assumed, and I think most people do, that those lines, those squiggles, represent neurons firing. That we're hearing the action potentials, the little electrical sparks of the brain cells.
That is the single most common misconception out there, and Ganong corrects it on page 1 of this whole section. The EEG is not recording action potentials.
It's not, but action potentials are the electricity of the brain. They're the signals. Why aren't we picking them up?
Think about the time scale and the distance. An action potential is like a gunshot. It's explosive. It's incredibly fast. We're talking milliseconds, and then it's over.
Okay.
Now imagine you're standing in the parking lot of a stadium, and inside are 100,000 people all firing guns, but randomly. You don't hear a rhythm, do you?
No, I hear static. Just noise.
You hear white noise. It's too fast and it's too chaotic to create a distinct, measurable wave that could possibly travel through your skull. The signal gets smeared.
So if we aren't hearing the gunshot, what exactly are we hearing?
We are hearing the echo of the crowd. We're recording the summation of dendritic postsynaptic potentials.
Okay, you're going to have to walk me through the anatomy of that. What is a dendritic potential and why can we hear that?
So let's visualize the cerebral cortex, that outer wrinkled shell of your brain. It's only about 2 to 4 millimeters thick, but it is packed with a very specific type of neuron called a pyramidal cell.
They call that because they're shaped like little pyramids.
Exactly. And the orientation here is absolutely crucial. These pyramids are all lined up in neat rows, like soldiers, with their points facing outward toward the skull. And from the wide base, they send these massive branching dendritic trees up into the surface layers of the cortex, specifically layers 1 through 4.
So it's like a forest. The cell bodies are the trunks down near the ground, and the dendrites are this thick canopy of branches tangled together up top.
Perfect metaphor. Now, when a signal comes into the cortex, let's say from the thalamus, which is the brain's relay station, it doesn't hit the trunk. It hits those branches in the canopy.
Okay.
And when it hits them, it causes ion channels to open. Positive ions flow into the dendrites. This is basic physics. Current flow creates a charge separation.
So the inside of the dendrite becomes positive, and the outside right next to it becomes negative.
Precisely. The dendrites at the top of the forest become negative relative to the cell bodies at the bottom. You have created a dipole, a tiny little battery.
And because millions of these pyramidal cells are all oriented in parallel, all pointing the same way.
They're tiny batteries summate. They add up. If they were all randomly oriented, their charges would just cancel each other out. But because they are all lined up in parallel, they create this massive fluctuating field potential that is just strong enough to travel through the cerebrospinal fluid, through the meninges, through the thick bone of the skull, and through your skin to the electrode we've pasted on your scalp.
That's incredible. So we're not measuring the firing. We are literally measuring the mood of the dendritic forest, the collective excitability.
That's a great way to put it. We are measuring the fluctuating tides of excitability in the canopy of the cortex. It tells us how close that patch of cortex is to firing, not whether it actually has fired.
But there's a catch, and Guyton calls this the volume problem.
Yes. The skull is a terrible conductor. It's an insulator. It smears the signal terribly. So for an EEG electrode to pick up any kind of coherent wave, you need massive synchronization.
You need a lot of neurons doing the same thing at the same time.
Millions of them.
Yeah.
It's not enough for them to just be active. They have to be active in unison.
And this leads to the most counterintuitive part of this whole topic, I think.
Yeah.
You would assume that when I'm wide awake, I'm solving a calculus problem. Or maybe I'm defusing a bomb in a movie.
High stakes.
My brain waves would be huge. I mean, I'm thinking hard, high power.
That's what logic would dictate. But if you look at the EEG monitor, when you are alert and focused, the signal is tiny. It's low voltage. It looks like chaotic, jagged fuzz.
Why? Why is it so small when my brain is so active?
Asynchrony. When you are alert, every little group of neurons is an individual. One group is processing the visual of the red wire. Another group is remembering the schematic you studied. Another is processing your fear about the timer. They are all firing incredibly rapidly, but they are firing out of phase with each other.
The cocktail party effect you mentioned earlier.
Exactly. Imagine a room with 1,000 people all having intense one-on-one arguments. If you hang a microphone from the ceiling, you don't hear distinct words, do you?
No, you hear a low, chaotic hum, a rumble.
Precisely. The individual waves are all canceling each other out, and that is the beta rhythm. High frequency over 14 hertz, but very low voltage. It's the signature of a busy, working brain.
Okay, but then I snip the right wire, the timer stops, and I close my eyes. I relax.
Now, the neurons stop processing all that distinct data. They begin to idle. And when they idle, they start to listen to the conductor. They sync up.
The cocktail party stops arguing.
And suddenly, the whole room starts chanting the same syllable, Om, Om, rhythmically, together.
And that synchronization creates amplitude. The waves get taller.
Huge amplitude. The individual signals aren't canceling out anymore, they're adding up. The waves on the screen get taller and slower. And this is the alpha rhythm, 8 to 13 hertz, the brain's idling state.
Who is the conductor? Who starts the chant?
The thalamus. This is really the heart of the system for many of these rhythms. The thalamus and the cortex are locked in this constant feedback loop. When you aren't actively engaging with the world, the thalamus starts beating a drum. It drives the cortex into this synchronous high-amplitude alpha rhythm.
The moment I open my eyes?
The sensory data floods back in, the light hits your retina, that signal goes to the thalamus, and the thalamus stops drumming and starts doing its main job, which is relaying information. The synchronization instantly breaks.
And the chant dissolves back into the cocktail party hum.
Exactly. The alpha waves collapse back into beta chaos. We call this alpha block, or the arousal response. You can see it happen in real time on a screen.
It's wild that we can see attention physically vanish from a monitor. It's the signature of the mind grabbing onto the world.
It really is. It's a beautiful demonstration of the brain shifting states.
Let's quickly fill out the rest of the waveform menu, just so listeners have the vocabulary. We've got beta, which is the working chaos rhythm. We have alpha, the relaxed, idling, synchronous rhythm. What about when things slow down even more?
Then you get into theta waves, 4 to 7 hertz. Now, in children, this is a totally normal rhythm to see, especially in the parietal and temporal lobes. But in an awake adult, it's a bit of a red flag.
What does it signal?
Emotional stress, frustration, disappointment. There are these fascinating studies showing that if you promise someone a reward and then you take it away, their brain throws a big burst of theta waves. It's the physiological signature of the damn it response.
I can guarantee I had some theta waves watching the game last weekend then.
I think we all did.
And finally, the basement level. The deepest rhythm, delta.
Delta, less than 3.5 hertz. These are monster waves. They are huge, rolling, high-voltage signals. This is the signature of deep, restorative, non-REM sleep. Or, if I see delta waves in an awake adult, that person has serious organic brain disease, a tumor, a lesion. Something is very wrong.
And there's an interesting distinction here that Ganong notes. Delta waves are different from alpha waves. They don't seem to need the thalamus.
That's right. It's a key point. You can surgically cut the connection between the thalamus and the cortex, and the alpha rhythm dies completely. It cannot exist without that feedback loop, but the cortex will still generate delta waves on its own.
What does that imply?
It suggests that the cortex has this intrinsic natural tendency to fall into this slow, rhythmic slumber if it's not constantly being prodded and stimulated by the outside world via the thalamus.
Which sets up the central conflict of our existence, really. If the cortex wants to sleep, if its natural state is this slow, synchronous rolling, what on earth keeps us awake for 16 hours a day?
That question, that single question, represents a huge paradigm shift in the history of physiology.
Okay, walk us through that history, the old way of thinking.
For a very long time, the prevailing theory was something called passive fatigue. The idea was just that the sensory neurons in the brainstem got tired. You use them all day, they ran out of neurotransmitter, the battery died, and the brain just passively shut down.
It makes a certain intuitive sense. I definitely feel like my battery is dying around 11 p.m.
It does, but it's wrong. And they proved it with some fairly brutal but informative experiments in the mid-20th century, the transection studies.
This is where they would surgically slice the brainstem of an animal at different levels to see what happened to consciousness.
Correct. And they made a shocking discovery. They found that if you cut the brainstem at the mid-pons level, the animal didn't fall into a coma as expected. The brain above the cut, what they called the servo-isolé, or isolated forebrain, it never slept. It was permanently hyper-alert. The EEG showed constant beta waves.
Wait, I thought cutting the brainstem was supposed to induce a coma.
It depends entirely on where you cut. By cutting at the mid-pons, they severed the connection to the sleep-inducing centers located in the lower brainstem, but they left the arousal centers in the upper brainstem intact and connected to the cortex.
So they proved that sleep isn't passive.
They proved it's an active inhibitory process. You have to force the brain to sleep. There are specific centers in your brain whose entire job is to actively shut down the arousal system.
So it's a battle, a constant civil war inside your skull.
It is a neurochemical seesaw, a constant push and pull. On one side, you have the ascending arousal system. This is the go team.
Okay, who are the players on the go team?
It's a big team. It originates in a network of neurons in the brainstem called the reticular formation. You can think of it as a fountain just spraying stimulants up into the entire cortex.
What kind of stimulants?
You've got norepinephrine coming from a tiny spot called the locus coeruleus. That's your alarm system, your vigilance. You have serotonin from the Raphia nuclei that helps maintain a stable mood and wakefulness. You've got acetylcholine from nuclei in the pons and midbrain that drives cognitive processing and learning. And then you even have histamine coming from the hypothalamus.
Which is why antihistamines make you drowsy. They block that signal.
Exactly. This is an incredibly powerful chemical cocktail. And what it does fundamentally is lower the firing threshold for neurons all over the cortex. It sensitizes them. It makes them ready to process incoming data. As long as this arousal fountain is on, you cannot sleep.
So how do we win the battle? How do we turn the fountain off and flip the switch?
We need a brake. And the brain's universal brake pedal is a neurotransmitter called GABA.
The great inhibitor. The stop sign.
Exactly. And there's a specific cluster of neurons in the hypothalamus. It's called the ventrolateral preoptic nucleus, or VLPO for short. Gannon just calls them preoptic neurons. These are the sleep snipers.
The sleep snipers, I like that.
They send these long axons down to the brainstem, and they release GABA directly onto all those arousal centers we just mentioned.
They inhibit the fountain.
They tell the locus coeruleus and the raphe nuclei to shut up. When those norepinephrine and serotonin levels plummet, the thalamus loses its sensitization. It stops relaying sensory data and starts that slow, drumming beat. The cortex syncs up, and you're out.
This mechanism where the sleep center inhibits the wake center and the wake center inhibits the sleep center creates a very specific type of behavior. It's called a flip-flop switch.
Right. It's bistable. The system strongly prefers to be in one of two states, fully awake or fully asleep. You don't want to be half slogging through the day. The mutual inhibition ensures a very rapid, clean transition between states.
But switches need a finger. Something has to push the button. Why do I get sleepy now at this particular time?
There are two main forces pushing that button. One is the master circadian clock, which we'll definitely get to, but the other is what we call homeostatic sleep drive. And basically, it's trash.
Trash.
Metabolic waste. Being awake is metabolically expensive. Your neurons are burning through ATP like crazy. One of the byproducts of that energy use is a molecule called adenosine.
And caffeine works by blocking adenosine receptors.
Precisely. As you stay awake, adenosine levels in your brain steadily rise. This chemical pressure builds up on those preoptic neurons, the sleep snipers, pushing them closer and closer to firing GABA and shutting the whole system down.
So the longer I'm awake, the more pressure builds to go to sleep.
Exactly. Guyton also mentions an older idea, a substance called muramyl peptide, that they found accumulating in the cerebrospinal fluid of sleep-deprived animals. If you take that fluid and inject it into a fresh, well-rested animal, it falls asleep instantly. So there's some kind of sleep factor that builds up.
But there is one more character in this cast that we have to mention, because when it's missing, the whole system just breaks down. Orexin.
Also known as hypocretin. Orexin is the great stabilizer. It's a peptide, a small protein, that's produced in a very specific part of the hypothalamus.
I've heard it described as the finger on the switch.
That is a perfect description. Orexin's job is to excite the entire arousal system. It keeps that switch firmly locked in the awake position while you are active. It's particularly responsive to things like motivation, hunger, and movement. It reinforces wakefulness.
And the best way to understand its importance is to look at what happens when it's gone. Narcolepsy.
Narcolepsy is a fascinating and, frankly, terrifying natural experiment. In most cases of human narcolepsy, it's an autoimmune disorder. The patient's own immune system has mistakenly attacked and destroyed the specific neurons that produce orexin.
So they have no finger holding the switch open.
Correct. Their flip-flop switch is incredibly unstable. It can wobble and flip at any moment. They can be wide awake, laughing at a joke, and that strong emotion is enough to suddenly snap the switch flips. But it doesn't just flip to normal sleep. It often crashes them directly into REM sleep.
Which involves paralysis.
Exactly, and that's cataplexy. The brainstem paralysis mechanism of REM sleep kicks in while they are still technically conscious. They just collapse. It's a stark reminder of just how fragile our grasp on consciousness actually is.
Speaking of REM, let's look at the architecture of a normal night. Because we don't just crash like a narcoleptic patient, we descend.
We take the stairs. This brings us to section 3, the architecture of sleep.
Okay, so I get into bed. I close my eyes, my brain's cocktail party quiets down, and the alpha rhythm kicks in. Then what?
Then even the alpha rhythm starts to break up and fragment. You drift into NREM stage 1. This is the transition zone. The EEG is low voltage, mixed frequency. If I tapped you on the shoulder right now, you'd probably jerk awake and claim you weren't sleeping.
I was just resting my eyes.
Exactly. But then you slide down into stage 2. This is arguably the most distinct and identifiable stage on the EEG because of two very clear signatures: sleep spindles and K-complexes.
What is a sleep spindle?
It looks like a boast of wire wrapped around a spool on the EEG trace. It's a quick zip of 7 to 15 hertz activity that lasts for a second or two. It's generated by that same thalamocortical loop that produces alpha waves.
Okay, but what is it doing?
We think it's the thalamus slamming the door on sensory input. It's a do not disturb sign for the cortex. There's good evidence that the more sleep spindles a person has, the harder it is to wake them up with external noise. It actively protects the sleep state.
And what about the other one? K-complexes.
A K-complex is this huge, high-voltage biphasic wave. It goes sharply down and then sharply up. They can occur spontaneously, but you can also trigger them by, say, making a small noise in the room. It seems to be the brain responding to a stimulus, but then deciding to suppress it and stay asleep.
So it's the brain saying, I heard that, but it's not important, going back to sleep.
That's the idea. So stage 2 is this light to medium sleep, characterized by these protective mechanisms.
And then we go even deeper, stages 3 and 4.
Welcome to the basement. This is slow wave sleep, the delta domain.
This is where that massive synchronization we talked about really takes over.
It's incredible. The waves are huge and slow, rolling across the cortex. And physiologically, this is the restorative phase. Guyton really emphasizes that this is when the body heals itself. Blood pressure drops significantly, respiratory rate slows, your overall metabolic rate plummets by up to 30%.
You're idling the entire engine to let it cool off and do repairs.
Precisely. And this is why if you wake someone up from stage 4 sleep, they are a complete mess. They experience what's called sleep inertia. They are confused, groggy, stumbling around. Their cortex is in such a deep state of synchrony, it can take several minutes to reboot to the asynchronous chaos required for wakefulness.
But we don't stay down there all night. After about 90 minutes, something really weird happens. We start to climb back up the stairs, and the EEG speeds up. It starts looking like beta waves again, like we're awake. But the person is fast asleep.
We have now entered the paradox. REM sleep, rapid eye movement.
Why do they call it paradoxical sleep?
Because the brain looks awake. In fact, as we said, oxygen consumption and metabolic rate in the brain during REM can be 20% higher than when you are awake and doing math. The brain is on fire with activity.
But the body is dead weight.
That is the critical safety mechanism. While the cortex is screaming with activity, vivid dreaming, emotional processing, the amygdala is highly active. The brainstem sends a massive inhibitory signal down the spinal cord to the motor neurons. It creates a total atonia. You are effectively paralyzed from the neck down.
Because if you weren't,
you would act out your dreams. You'd be running from monsters, fighting, flying. And there's a clinical condition called REM behavior disorder where this paralysis mechanism fails. These patients, usually older men, will tackle their dressers, punch their spouses, dive out of bed. It can be incredibly dangerous.
Ganong mentions a very specific electrical signature for REM sleep called PGO spikes. What are those?
PGO stands for pons geniculate occipital. These are very sharp, high-voltage spikes of electrical activity that originate in the pons, which is part of the brainstem. They then shoot up to the lateral geniculate nucleus of the thalamus, which is the brain's main visual relay station.
And then to the occipital cortex.
And then they land in the occipital cortex, which is the visual processing center at the back of your brain.
So the brainstem is literally shooting electricity directly into the visual cortex.
It's thought to be the spark of the dream. You are stimulating the visual system from the inside out. That's why REM dreams are so intensely vivid and visual. You're not seeing with your eyes. Your brain is creating an internal virtual reality. The primary visual cortex is off, but the association areas are lit up.
And the body goes haywire during this, right? It's not peaceful.
Not at all. It's an autonomic storm. Your heart rate becomes irregular. Your breathing becomes shallow and jagged. You lose your ability to thermoregulate. You become poikilothermic, like a reptile. Your body temperature just drifts toward the room temperature. It is a very chaotic, fragile state.
And we cycle through this, from light sleep down to deep sleep, up to REM, and back again, every 90 minutes or so.
Yes, these ultradian rhythms drive our night, but the ratio changes dramatically. In the first half of the night, you spend most of your time in deep, slow-wave sleep. Your body prioritizes physical restoration first, fix the muscles, clear the waste.
And then later on.
Then, as the night goes on, the periods of deep sleep get shorter and shorter and eventually disappear. And the REM periods get longer and more intense. By 6 a.m., you are spending most of your sleeping time dreaming, which is why you usually wake up from a dream.
This incredible timing, the 11 p.m. sleepiness, the 7 a.m. wake up, the 90-minute cycles, it doesn't just happen by accident.
Yeah.
We have a master clock.
The suprachiasmatic nucleus, the SCN.
I love the name because it's literally a GPS coordinate in the brain, suprachiasmatic.
Above the chiasm. It is a tiny cluster of neurons in the hypothalamus that sits directly on top of the optic chiasm, which is a point where the optic nerves from your two eyes cross.
And it's sitting there for a very specific reason. It's wiretapping the phone lines coming from the eyes.
Exactly. The SCN is an incredible internal oscillator. Even if you were to live in a dark cave with no light cues at all, your SCN would keep a rhythm of about 24 to 25 hours. It has its own internal clock genes, But to match the Earth's precise 24-hour day, it needs to be entrained. It needs a reset signal every morning, and that signal is light.
But it's not using the rods and cones that we use to see shapes and colors, is it?
No, and this was a huge discovery. There's a special third type of photoreceptor in the retina, specific ganglion cells that contain a light-sensitive pigment called melanopsin. They don't care about shapes or colors. They are basically lux meters. They just measure ambient brightness.
And they have a direct line to the boss.
A direct line. It's called the retinohypothalamic tract, and it goes straight from these cells in the retina to the SCN. It's a private line that just says one of two things: sun is up or sun is down.
And when the SCN gets the sun is down signal, it initiates the darkness protocol, the melatonin pathway.
Yes, and Ganong maps this route out, and it is just absurdly complicated. It's a complete Rube Goldberg machine.
It is. You'd think the SCN would just send a chemical message to the pineal gland, which is right next door in the brain, and say, hey, it's dark, make some melatonin.
But it absolutely does not do that. For whatever evolutionary reason, the signal takes the scenic route. The SCN signals another part of the hypothalamus, the paraventricular nucleus. That nucleus then projects its axons down the spinal cord to the intermediolateral cell column.
So we've left the brain entirely.
We're in the spinal cord. Then the signal goes out of the spinal cord to a cluster of nerves in the neck called the superior cervical ganglion.
We are in the neck now.
We are fully in the neck. And then sympathetic nerve fibers from that ganglion in the neck travel all the way back up, piggybacking on blood vessels to re-enter the skull and finally innervate the pineal gland in the brain.
It's completely bizarre.
Yeah.
But once the signal finally gets there, it triggers a fascinating chemical factory. The nerve endings release norepinephrine onto the pineal cells.
And this is the molecular switch that Ganong details so beautifully.
Right.
That norepinephrine hits beta-adrenergic receptors on the pineal cells. This causes a massive spike in the levels of a second messenger called CAMP, cyclic AMP, inside the cell. That CAMP then activates a specific crucial enzyme, N-acetyltransferase.
And this is the rate-limiting step, the bottleneck in the process.
This is the worker on the assembly line that determines the speed of production. This enzyme's job is to grab serotonin, which is abundant in the pineal gland, and convert it through a couple of steps into melatonin.
So darkness literally causes our brain to turn serotonin into melatonin.
Correct. And melatonin is the vampire hormone. It only comes out at night. It then circulates through the blood and floats back to the SCN, where it hits special MT1 and MT2 receptors to help synchronize the clock and promote sleepiness.
And this explains perfectly why staring at a bright blue phone screen at night is such a disaster for sleep.
It's a complete disaster. If you stare at a bright LED screen at 11 p.m., that blue wavelength light is preferentially firing that retinohypothalamic tract. You're sending a powerful sun is up signal to your SCN.
Even though it's midnight.
The SCN believes the light. It shuts down the entire pathway to the pineal gland. The norepinephrine release stops. The CAMP levels drop. That key enzyme, N-acetyltransferase, turns off. And you stop making melatonin.
You have chemically jet-lagged yourself without ever leaving your sofa.
Precisely. It's a powerful and often disruptive system.
Okay, we've talked about how the system works when it's functioning properly. Now let's talk about what happens when it fails. We discussed the forest of electrical activity earlier. What happens when that forest catches fire?
Epilepsy.
And Ganong has a great definition: uncontrolled, excessive synchronous firing.
It's a feedback loop that's gone completely wrong. Normally, the brain maintains a very delicate balance between excitatory signals, mainly the neurotransmitter glutamate, and inhibitory signals, mainly GABA. In a seizure, either the gas pedal gets stuck down or the brakes completely fail.
Let's distinguish between the two main types that the books cover: focal and generalized.
A focal seizure, or what used to be called a partial seizure, starts in one specific spot. Maybe there's a little bit of scar tissue from an old head injury or a bike accident. The electrical storm is initially contained to one area of the brain.
But it can move. Guyton describes the Jacksonian March, which is a terrifyingly vivid concept.
It is. Imagine the seizure starts in the part of the motor cortex that controls your thumb. Your thumb might start twitching uncontrollably. Then the electrical storm spills over into the neighboring neurons that control the hand. Then the hand starts to jerk. Then it moves to the arm, then the shoulder, then the face. You can literally watch the seizure march up the person's body as the electricity marches across the physical map of the brain.
But if that electrical storm happens to hit the thalamus?
Then it goes nuclear. The thalamus, remember, is the great relay station. If the seizure activity gets into that thalamocortical loop, the thalamus broadcasts the seizure to the entire cortex on both sides simultaneously. This is a generalized seizure, the classic grand mal.
The tonic-clonic seizure.
Yes, the tonic phase is first. That's when every muscle in the body contracts at once, causing rigidity. That's the signature of a high-frequency, continuous discharge across the brain. Then comes the clonic phase, the violent, rhythmic jerking.
And that's not just random shaking, is it?
No, it's actually the brain's inhibitory neurons trying to fight back. They are firing furiously, trying to chop up the seizure signal, which causes these rhythmic breaks in the contraction. It's the physiological sign of the brain trying to regain control.
There's one very specific type of generalized seizure that Ganong mentions that I find fascinating because the mechanism is so precise. Absence seizures. What used to be called petit mal.
Yes, the blank stare. You see this most often in children. They'll be talking or playing, and they just check out for 10 seconds. They stare blankly. There are no convulsions. They're just gone. And then they pop right back in and have no idea anything happened.
And the EEG shows this very specific, very clean 3 Hz spike and wave pattern.
Yeah. And we know exactly why. It's caused by an oscillation in a specific type of ion channel in the thalamus. They're called T-type calcium channels. They get into this rhythmic oscillating state that drives that 3 per second pattern in the cortex.
Why does that molecular detail matter so much?
Because it dictates the cure. We have a drug, ethosuximide, that specifically blocks those T-type calcium channels. It is incredibly effective for absence seizures, but does absolutely nothing for grand mal seizures. It's a perfect example of how understanding the specific molecule leads directly to the specific medicine.
Let's pivot from an electrical failure to more of a mechanical failure. Sleep apnea. This isn't really a brain problem to start with, is it?
Initially, no. It's a plumbing problem. It's a throat problem. Remember that muscle paralysis, the atonia of sleep? Well, for millions of people, especially as they get older or gain weight, the muscles that hold the airway open in the back of the throat relax too much. Gravity takes over. The airway collapses.
You choke.
You stop breathing. Sometimes for a minute or more. Your blood oxygen levels plummet. Your CO2 levels spike. The chemoreceptors in your body scream in panic to the brainstem. The brain has no choice but to trigger a massive arousal response, a surge of norepinephrine, to wake you up just enough to take a gasp of air.
And this can happen hundreds of times a night.
Hundreds of times, and the person is usually completely unaware of it, but you completely shred your sleep architecture. You never get into that deep restorative delta sleep because you are constantly being dragged back to the surface to fight for air. You wake up exhausted with high blood pressure and at a much higher risk for stroke and heart attack. It is a physiological disaster.
One last category of failures, the things that go bump in the night, the parasomnias, sleepwalking, night terrors.
These are very spooky. And the key thing to remember from the text is that they almost always happen in NREM sleep, specifically in deep, slow-wave delta sleep, stage 4.
Wait, I thought we acted out our dreams in REM.
No, in REM you are paralyzed, or you're supposed to be. That's REM behavior disorder. Sleepwalking happens in the basement, stage 4. What seems to happen is the brain gets stuck in a bizarre hybrid state, halfway between deep sleep and wakefulness. The motor centers of the brain turn on, but the conscious thinking parts of the cortex, the frontal lobes, are still fast asleep.
So the lights are on, but nobody's home.
Literally. That's why you can't reason with a sleepwalker and why it's so hard to wake them up. They're chemically in the deepest possible state of sleep, even though they are physically up and walking down the stairs.
Okay, so we have covered the physics, the chemistry, the architecture, and the pathologies of this system. We have to ask the final, ultimate why. We spend a third of our lives in this vulnerable, unconscious state. Evolution is usually ruthless about efficiency. Why haven't we evolved out of sleep?
It must be doing something absolutely vital, and Guyton and Ganong both offer a few compelling theories. The first and most obvious is simple restoration.
The brain's cleaning crew comes in.
Right, the glymphatic system. During sleep, the space between brain cells actually expands, allowing cerebrospinal fluid to flush out all the adenosine, the beta amyloid, and the other metabolic trash that built up during the day.
There's also energy conservation.
Yes, in a food-scarce ancestral environment, dropping your metabolic rate by 30% for 8 hours every night is a significant survival advantage. You save calories.
But there is a more complex and I think more interesting theory that Guyton touches on in the context of memory. It's about the librarian.
Memory consolidation. This is the big systems level view. During the day, your hippocampus, the librarian, is busy taking in new books, new experiences, short-term memories, but it has very limited shelf space. It can't hold everything forever.
So sleep is when the librarian files the important books away in the main library.
Sleep is when the hippocampus has a long conversation with the neocortex, which is the long-term archive. It essentially replays the important events of the day. We can see this in the brain activity of sleeping rats. It decides what information is worth keeping and initiates the slow process of moving it to permanent storage in the cortex.
But perhaps more importantly, it also decides what to throw away.
Exactly. This is a newer idea, the synaptic homeostasis hypothesis. The idea is that during the day, as you learn, your synapses get stronger and stronger. They potentiate, they get saturated, they get noisy.
You can't just keep turning the volume up forever.
You can't. At some point, you can't learn anything new because all the circuits are already at maximum strength. So sleep is a process of downscaling. The brain systematically and intelligently weakens the synapses that weren't important or frequently used. It clears the noise to preserve the signal. We wake up with a fresh slate, ready to learn again.
Which means if you don't sleep after studying, your slate is already full. You literally cannot learn anything new the next day.
Correct. You need the off rhythm to maintain the capacity for the on rhythm.
It brings us right back to where we started. Consciousness isn't a static thing. It's a rhythm. It's this delicate oscillating balance of chemicals and electricity.
And your memories, your personality, your ability to think clearly are just the emergent result of that oscillator being tuned correctly night after night.
So here is the thought I want to leave our listeners with.
Yeah.
We tend to resent sleep, don't we? We treat it like a waste of time, an inconvenience to be minimized. But if these theories are right,
then sleep is the only reason you exist at all.
without that nightly reorganization, without that clearing of the noise, the continuous stream of consciousness that you experience would just dissolve into static.
The rhythm is the reality.
Something to think about when you turn off the lights tonight. Visualize the dendrites, feel the dipole, and let the GABA take over.
Go get some delta waves.
Thanks for listening to The Deep Dive. We'll see you next time.